Have you ever looked down at a trail of ants and wondered, where are they all going? What's hidden beneath that busy line of tiny bodies? The truth is astonishing. Beneath our feet, ants build cities. Not simple burrows, not random holes, but sprawling metropolises with highways, storage rooms, farming chambers, nurseries, ventilation shafts, and even waste treatment zones. Some of these underground empires stretch meters deep and house millions of individuals. And here's the real marvel. No single ant has the plan. No leader commands the workers. Each ant follows just a handful of rules, guided by chemical signals and environmental cues. Yet together, they create architecture so advanced that human engineers are studying it for inspiration. Scientists call this principle stigmergy. It means coordination through traces left in the environment. One ant drops a soil pellet, and another is more likely to drop one nearby. A chemical trail is laid, and others reinforce it. Small decisions ripple outward, and slowly, a city takes shape. But how do they actually do it? Let's step inside the world of the ant architects. Ants don't have concrete, steel, or blueprints. They have soil. But even dirt is a complex material. A tunnel's stability depends on the size of the grains, how moist the soil is, and how compacted it becomes over time. Too dry, and walls collapse. Too wet, and the mud clogs their mandibles. Ants instinctively dig where the soil is at just the right sweet spot, moist enough to bind together, dry enough to move. And here's something fascinating. Tunnels are almost always about one ant body wide. Why? Because that width minimizes excavation effort while still letting traffic flow in both directions. Workers can even brace themselves against the walls when carrying heavy loads. With every trip, their bodies polish and compact the surface, making the tunnels stronger, a self-reinforcing design that requires no central control. Some species go further. They mix soil with saliva or plant resins, creating a natural cement. Wood ants, for instance, add conifer resin to their mound structures, which doesn't just strengthen them, it also acts as an antimicrobial shield, protecting the colony from disease. Now imagine a city designed not only for the ants themselves, but for their crops. Leafcutter ants build some of the largest subterranean structures of any insect. They dig hundreds of chambers connected by highways, all dedicated to one purpose: farming fungus. But fungus is picky. It requires precise temperature, humidity, and airflow. So the ants regulate their cities with a form of natural ventilation. On the surface, they build turrets. Wind blowing across these porous towers draws warm, carbon dioxide-rich air up and out, while cooler, oxygen-rich air flows in through other openings. It's natural air conditioning, millions of years before humans invented HVAC systems. Inside, the colony is carefully zoned. Gardens are kept in the most stable chambers. Trash is dumped in separate waste pits, quarantined from the food supply. The queen and her brood are placed in the cleanest, most secure chambers. It is a city not only of construction, but of public health. But not every ant builds underground. In tropical forests, weaver ants build in the treetops. Their materials? Living leaves, their glue, silk spun by their own larvae. Workers form chains with their bodies, pulling the edges of leaves together. Others carry larvae across the seam, pressing them down so they release silk, stitching the leaf walls shut. The result is a suspended chamber, flexible enough to sway in the wind, cool enough to resist the tropical heat, and expandable whenever the colony needs more room. And they don't stop at one nest. Weaver ants create entire networks of these leafy chambers, connected by branches like a city in the sky. Then there are the army ants. Nomads of the insect world, they don't build permanent nests at all. Instead, they build out of themselves. At night, thousands of ants interlock their legs to form a living bivouac, a pulsing, breathing fortress that shelters the queen and brood. The structure flexes with the environment. If it gets too hot, the ants spread out and open ventilation pores. If it gets too cold, they cluster tightly, sealing the walls. Army ants also build bridges with their bodies, spanning gaps to keep their foraging columns moving. These bridges aren't fixed. They lengthen, shorten, and dissolve depending on traffic flow. When prey is abundant and speed matters, more ants join the bridge, creating shortcuts. When traffic slows, the bridge vanishes and the ants return to foraging. It's real-time architecture, constantly adapting to need. Fire ants take architectural ingenuity even further. When floods hit, they weave themselves into rafts, living waterproof platforms that can float for weeks. Air is trapped between their bodies, keeping the entire colony buoyant, even protecting the queen deep within the raft. In confined spaces, they build vertical towers out of their own bodies, shifting weight among themselves to prevent collapse. Underground, they dig vast branching tunnels that remain remarkably uniform in diameter. If a blockage occurs, ants reroute, dig alternate channels, and reopen flow, maintaining the city's circulation. So what drives all this complexity? At the core are simple, universal rules. Ants tend to deposit soil where other soil has already been deposited, positive feedback that builds walls. But when structures get too steep or unstable, deposition stops, a natural break. Tunnel width emerges from collision frequency. If ants bump into each other too often, they widen the tunnel. If collisions are rare, they leave it narrow. Ventilation emerges from differences in wind, pressure, and temperature. Ants don't design airflow, but by opening or sealing entrances, the colony naturally adjusts to create circulation. Environmental cues act as templates. Ants are drawn toward moisture, away from light, and into spaces that vibrate less. These tendencies ensure that nests are dug in places that are stable, safe, and easy to maintain. And redundancy ensures survival. Multiple entrances, waste chambers, and escape tunnels make the system resilient. If part of the city floods, burns, or collapses, the rest carries on. We like to think of ourselves as the ultimate builders. But ant architecture has lessons for us. Data routing algorithms are inspired by the way ants lay pheromone trails. Decentralized construction robots now mimic the way ants deposit pellets of soil. Even hospital zoning and ventilation design borrow ideas from the way ants separate clean food and waste chambers. Fire ant rafts and bridges inspire ideas for self-assembling structures that could help humans in disasters or space exploration. Across the ant world, architecture takes countless forms. Wood ants build towering thatch mounds that use solar energy for heating. Harvester ants dig deep shafts with side chambers for seed storage. Tiny temnothorax ants choose and renovate hollow acorns with collective decision-making that rivals parliamentary debate. Carpenter ants carve polished galleries into wood, remodeling fallen trees with exquisite precision. What ants teach us is that intelligence isn't only in the mind. It can emerge from interaction, from simple rules repeated thousands of times, from feedback between builders and their environment. No single ant knows the city, yet the city stands. The architect is not an individual, but the colony itself. The blueprint is not drawn on paper, but in soil, silk, resin, and even living bodies. So the next time you pause to watch a trail of ants marching across the ground, remember, you're not just watching insects. You're standing above a civilization, an underground metropolis, or a canopy city, crafted by some of the most remarkable architects on Earth. Tiny, tireless, and brilliantly efficient, the ant architects.